Okay, this is Third Rock from the Sun, video 3. We're going to go through actually just the earthquake section in today's PowerPoint, and there are a ton of pictures. Okay, so earthquakes are one of the most destructive forces on Earth, geologic forces on Earth. The earthquake itself is not destructive. You'll be shaken around, but it won't necessarily injure you. The injuries and the deaths come in because it's the buildings and the structures, human structures, that get destroyed, and then they cause, in that process, they cause injury and death, not the earthquake itself causing injury or death. So these are just, some of the more recent ones that had such a big impact, and the number of people that died. Okay, so there's about 30,000 earthquakes worldwide every year that are strong enough to be felt. But only 75 of them are significant earthquakes. So it's happening. This earthquake movement, as the plates shift around, is happening very, very regularly. And these are only the ones strong enough to feel. There's probably a whole lot more that we can't feel, but the significant ones are fairly rare. This is one in 1906. Took 1 to 2 seconds, and then you see that shift where the fences no longer match up. Okay. So an earthquake is a vibration of the earth. It's the rapid release of energy from seismic, or in the form of seismic waves. It moves in all directions, so you have that central source, that focus, which is right here, usually underground somewhere, and then the waves move out just like any wave would, moves out from that. So it's like a stone in a pond causing the ripples. Energy dissipates with distance until it's all used up. They don't happen randomly. We've already talked about the plate tectonics theory, where they occur on the fault lines, the fracture lines inside the Earth, and on the plate boundaries. Sometimes it happens in the plate interiors if there's enough stress built up, but most of the time it's the plate boundaries. Okay, so the elastic rebound theory is that the forces of the earthquake, the energy, will bend the rock on either side of the fault. The rock, is more and more stressed as time goes on, and slow strain that's increasing and increasing until you hit that imaginary or invisible boundary where the weakest point can't handle the stress anymore and it breaks. The break sends out the shock waves. They migrate from the original break, and that causes the shaking. The stress with that release of energy is released, and so then the aftershocks are adjustments to that change in stress. The aftershocks are always less strong to the main shock, but sometimes they actually cause more damage because you have this structure, this building or bridge or whatever it is, that's weakened by the main shock, and then when another shock hits it, that is again just enough to put it over the edge to cause significant damage and therefore perhaps injury to people. Okay, so the fault mechanics of how that elastic rebound cycle, how it causes earthquakes. So you have an earthquake, and everything is kind of set back to zero, where you have no stress, no problems, straight line, everything's good. This is at the plate boundary. And then you have this buildup where the plate boundaries are moving, and you see that kind of where it messes up, where you have that strain. You can see that strain where everything is not lining up so well. And then after the slip, you see where this tension is released. Now, instead of being curved, it's straight. So the behavior is an interaction between two different systems, the rock surrounding the fault and the rock in the fault zone. So the rock surrounding the fault, which would be, if you're looking at it, all of this stuff around, like over here and over here, that's the elastic distortion, like a spring. It kind of bends and then moves back. But then in the fault zone, you have a frictional sliding where you actually have a shift and a movement. So if you're looking at an earthquake area, you see where it shook a little bit, but everything moved back to normal. And then you have the frictional sliding where you have new earth, new, separated apart, difference, some kind of difference, however you want to describe it. Okay, so you see the extensional is moving away, the compressional is moving toward, and the transform is sliding past each other, to review from the first two videos. Okay, The duration of shaking tends to be relatively small. Kind of depends on how much stress is built up, how much energy is stored, how high the magnitude of the earthquake, stuff like that. Less than a minute is usually, or is the average, is very usual. The 1962 quake in Alaska set a record at 4 minutes. So the types of waves, the earthquake waves are seismic waves, and we record them on seismometers, which are on seismographs. Oh, you're noticing the trend here. Okay, so the surface wave obviously travels on the Earth's surface, moves away from the epicenter. So they're very slow, they cause a lot of damage. It's that rolling feeling. I don't know if you guys have ever been in an earthquake, but it's a rolling feeling. The body waves travel through the interior and they spread out from the focus. So the body wave will move up until you hit the surface wave. So body waves are divided into P waves and S waves. The P waves is pressure or compressional waves. They vibrate parallel to the direction of wave travel like a slinky. They travel really fast, 4 to 7 kilometers per second. And P is primary. It's the first wave that hits at the recording station. And then S waves are the shear waves. They vibrate perpendicular to the direction of wave travel like the snapping of a rope. And they're slower than the P wave, 2 to 5 kilometers per second. It comes second. It's a second wave to come in after the primary wave. So to help you guys remember all this, I would make like a little table or something to remember the different types of waves, when they hit, what order, so that you can walk through like an imaginary earthquake and make sure that we can do that. Okay, so if you're looking at a seismograph reading, you see the P waves and the surface waves, and then you can tell the primary and secondary. You see that primary hit, that big jump in energy, and it settles out, and then a secondary jump in energy, the same here. Sometimes it's bigger than the other. So it just kind of shows you, the various options of different recorded times and different quakes. Okay, so the epicenter of an earthquake, how to find the epicenter of the earthquake. You have to look at the way the waves are traveling. So they all start out, P, S, and surface waves, all start out at the same time. The further away you are from the quake, the longer the time span between them, because remember the P and S wave have different speeds. So you can calculate the distance of the seismometer to the earthquake by the time between the arrival of the P wave and the arrival of the S wave. Just a little bit of algebra, and you can figure out that, remember, velocity is distance divided by time. If we have the velocity, we have the time, we can figure out the distance. But we can't tell the direction. So we know that it's, for example, 20 miles, but we can't figure out 20 miles where that earthquake started. So we have to use multiple sites. And that way we can figure out if you have point A, point B, and point C, and then you know that it's 20 miles, you can draw lines and mark off 20 miles until they all intersect, a 20-mile radius. And I think I have, yes. Okay, so this is what they do. So they say, this is our seismometer right here, seismometer right here, seismometer right here. So we know that the earthquake was 2,800 kilometers from this seismometer. So in any direction, 2,800 kilometers. It was from this seismometer 4,800 kilometers. So we draw a circle any direction 4,800 kilometers away. And then a radius of 34 kilometers from this seismometer, anywhere, whatever direction. So then where those three circles line up, intersect, that's where the earthquake happened. And you can see, coincidentally, oh look, it's right on a plate boundary. Okay, so this shows some of the, remember this would be like the slinky, where you see the distortion, but you don't see any of the slip, the movement. So this is a distortion, but it didn't actually move. I'm going to go through a whole lot of images of different earthquakes. So this would be actually where you see Earth moved. Obviously the road is no longer there. Same here where we have a nice fault line. This is a 1906 earthquake in San Francisco. And you see those houses tilted. Secondary events. So the San Francisco earthquake started a lot of fires. So again, it's not necessarily the earthquake that does the damage; it's the human structures and the damage from those structures. So when gas lines slipped and moved around from that shock wave, that started fires, and then the fires were very, very destructive in the San Francisco earthquake. In Anchorage, Alaska in '64, that was that one that had such a huge, that 4-minute waves were felt for 4 minutes. Very, very destructive. You can see the difference there. More of the Anchorage, Alaska. It was absolutely insane amount of energy released. A lot of flood damage, tsunami damage. So again, earthquakes a lot of the times will cause tsunamis, which is that big wave, that energy released hits a whole bunch of water. The water picks up that energy, and that translates into a tsunami, which is a really big wave. So the tsunami damage, the waves can be very destructive. This is still that 1964 Alaska in different places. Here you can see really clearly where the structure actually slipped, as opposed to it bent, but it did not actually move. A landslide. Landslides are very common, and again, that's what would cause a tsunami. So you have the shaking, you have this landslide here. Once all that hit the water, you see the wave moving out from there. Same landslide, another example of a landslide problem. Okay, and that is it for earthquakes. So that is the end of this video.